Sende olunca ben çok şey yapıyorum. Tamamdır. Yes, class. Online classes here and yesterday we stopped at L'Hôpital's rule, which you already know from your pencereleri açar mısınız? L'Hôpital's rule. Burada daha önce ders yok herhalde. You remember L'Hôpital's rule from your calculus classes, okay? So you will use it extensively in when you take the, remember this formula that we mentioned yesterday. We take the limit as n goes to infinity, and we take the ratio between the two functions, and by looking at this result, we can determine the complex class in many cases, if not most. So while taking this limit, we may frequently encounter infinite over infinity type situations, in which case we use L'Hôpital's rule to arrive at meaningful results. So let fx and gx be functions that are differentiable. Kayıt alabilir misiniz? Alıyor musun? Süper. That are differentiable. So this is also one of the important things here. Sometimes we may not be able to take the derivative, okay? With some, especially if it's a discrete function, etc. But we don't have these in running times because it's in real time. Remember, the function is from the set of natural numbers to the set of real numbers because the running times are usually continuous time. So are differentiable for sufficiently large numbers. Numbers x. If limit as n goes to infinity, fx is infinity, and limit as n goes to infinity, gx is infinity, or if limit as n goes to infinity, fx is 0, and limit as n goes to infinity, gx is 0, then we have this following result. High school mathematics, basically. Limit as n goes to infinity, fx over gx is equal to the derivative of these functions. One frequent mistake that I usually see in almost every year is just that you memorize how to take derivative as you memorize only the case x to the power some constant, okay? And then you do it constant times x to the power constant minus 1. So if it's x cubed, you make it okay, 3x squared, which is okay, which is true. But you don't really pay attention to whether it's actually in that form or not. I mean, I don't want to say all of you, but a lot of you, let's say. Even if it's an exponential derivative or some other function, just treat it as a polynomial and apply the same logic, which was memorized anyway, okay? So pay attention to what you're taking the derivative of, okay? So don't just apply the frequently used case to all cases. F prime x over gx. So properties of these complexity classes is that let Fn and Gn be a set of functions. Fn and Gn be an element of this calligraphic F, which is the set of functions, okay? So if, sorry, not if, Fn is in big O Gn, if and only if, what can be the relation between Gn and Fn? If Fn is in big O Gn, then Gn is what? In which complexity class of Fn? Sorry? What O? No, Fn is big O in big O Gn. What about Gn? Gn is also big O Fn? That was the theta case, which was the equivalence relation. Now it's omega. Which omega? Big omega, right? If Gn is an upper bound to Fn, then Fn is a lower bound for Gn, right? Okay. So now what you said, Fn is in theta Gn. They grow at the same rate, means that Gn is also theta Fn, okay? They are in the same class. Yeah, they're in the same class. And that's why it was an equivalence relation, the theta relation. There is this symmetricity of, property, which is not the case in the other complexity classes. So Fn is in theta Gn if and only if, so it means this is true both ways. If Fn is theta Gn, then this is true, but also that part is also true, okay? Fn is in theta Gn if and only if Fn is both in big O Gn and omega, big omega Gn, okay? So if somebody asks us to prove that a certain function is in the complexity class theta of some other function, what we actually need to prove is that first we need to prove that it's in big O and also omega. This is analogous to saying that, for instance, if somebody asks you to prove that A is equal to B, how do you prove it? The formal way of proving it is that first you need to prove that A is less than or equal to B and A is greater than or equal to B. So if and only if both of these are true, it means what? It means they're indeed equal to each other, right? So this is more or less like that. That was the, they are the relational operators, but we don't have the relational operators here, but the behavior is similar if you need to remember. So another property is that Fn is in little o Gn if and only if, what can I say now for the relation between Gn and Fn? Gn is in which complexity class of Fn? Fn is little o Gn, then Gn is, excuse me, little omega, yes. Because of the masks, your voice is not as loud as they were without the masks, okay? Same thing for me, that's why it's very difficult to make a lecture with these masks. But easier than I thought it would be, for some reason, I don't know. So if Gn is a strict upper bound for Fn, then Fn is a strict lower bound for Gn, right? This is like that. If A is less than B, then B is definitely greater than A, or the reverse. So if Fn, now okay, Fn is in little o Gn. Now this is only one way. Then it's also true that Fn is big O Gn, right? But the reverse, not necessarily, okay? So that's why this is just one direction. 2 is less than 3 means that 2 is also less than or equal to 3, right? But the reverse does not always have to hold because they might have the equal complexities also. And similarly, now this time, if Fn is big omega Gn, then Fn is little omega Gn, right? Not the reverse. So with theta, we need to say that given a constant, given a positive constant, theta Fn is equal to, now I can say equal to because we are talking about the equality of two sets. We mean that these are the same sets actually, okay? Now we can use the equal sign. Is both, because both of them are sets. In the functions, one of them was a function and the other was a set of functions. That's why we use the element of sign. Theta Fn is equal to theta C times Fn. Because C doesn't matter in the complexity class, so we can, theta n is indeed the same as saying theta 2n, theta 3n, whatever, as long as it's a positive constant, okay? For 0, it's not true. For C is equal to 0 is not permissible. So also true for other symbols. Let's note that. Also true for other complexity classes, let's say. Except this very rare complexity class, which was tilde. Remember what tilde was? I think we talked about it yesterday. We said that it's just if the constant is 1 here. Here. This is the good thing about using OneNote. I can that was not the thing when I in the actual class when I used the actual whiteboard. We said that this is, if this ratio is exactly equal to 1, then it's tilde, which is a special case of this theta, okay? In the theta, we said that it's C, and C is a positive constant. We said that. But with tilde, is a special case of that. That's why it's not true for tilde, because when I multiply it by a constant, then it's not 1 anymore. It's some other complexity class. Okay, so tilde is the most rare one. You probably won't even hear about it except this class. And in this class, we mention it just to say that, okay, there's something like this, okay? Just for you to remember, we're not going to use it extensively anyway. And I don't understand why it is important. I mean, I haven't seen any useful application of defining a separate class for a constant one. Anyway, okay, another property. Fn is in big O Gn. So these notations always indicate sets and classes, okay? If and only if, this is an important property, big O Fn is a subset of big O Gn, okay? So maybe to remember it, we can think of it in an example, okay? Let's say that n is a function like fn is n, and gn is n squared. So n is in big O n squared, right? Which is true. N is also in big O n, but I just wanted to give different functions because they don't have to be the same. Otherwise, you would think that you could think that they will have to be the same. But this also means that big O n is a subset of big O n squared. Okay? Because it's like a low order terms also in this set. Because it's also an upper bound. Okay? So this is another property, and we have similar properties for the other complexity classes as well. Online class, can you hear me properly?
Yes.
Yes.
Okay. So, Fn is in little o Gn. If and only if, with little o, we don't have this subset sign. Now we need to have a strict subset. Okay? If Fn is strictly upper bounded by the set of functions Gn, the growth rate of Gn, okay? Then it means that big O Fn is a proper subset of big O Gn, okay? Proper subset. What were we saying this in Turkish? Subset alt küme, proper subset. Öz alt küme. İlk önce öz alt küme olarak öğrendik herhalde size. Bilmiyorum, yabancı liseden gelmediyseniz ya da öyle değildir. Öz alt küme. Fn is tilde Gn. If Fn is tilde Gn, then Fn is also theta Gn, because remember, tilde is a special case of theta, where it's exactly, even the constants are also equal to each other, right? That's why, but it's not the other way around. It's just this way, okay? The reverse does not need to be true, okay? It need not always hold. Big O Fn is equal to big O Gn if and only if theta Fn is equal to theta Gn. We are now talking about the equality of two sets, okay? If and only if, again, omega Fn is equal to omega Gn, okay? So this is like three-way of inequality, three-way of if and only ifs. So this if and only if is true, this if and only if is true, which also means that the if and only if between big O and big omega is also true, okay? So any questions up until here? Now I will continue with some other definitions and some remarks. Given two functions Fn and Gn, Fn and Gn have the same order if Fn is in theta Gn. Okay, we say that they have the same order. Fn has a smaller order than Gn if big O Fn is a proper subset of big O Gn. Okay, so this is like the same as saying Fn is in little o Gn. Okay, and or in other words, Gn is in, yeah, okay, that's not necessary. Okay, So a question for you, between any given two functions, okay? You're given any two functions. Is it always possible to determine a complexity class relation, like big O theta omega relation between the two? Does it have to be any one of these, or can it be the case that this cannot be defined between a specific two functions? Like any two functions, is it possible for them to exist so that defining a complexity class relationship between the two is impossible?
The function is all over the place, like going up and down, up and down. Maybe it is
like sinusoidal function. Lower bounds, which are constants, okay? Yeah, functions involving modulo operators, for instance, not sinusoidals, they are in constant class, but modulo operators, like mod 3, mod 4, whatever that mod is, then there is not any definite, because you cannot find that n0 point, so that up from that point onwards, everything is manageable, okay? Or it's possible to say something at least from that point onwards. But because modulo functions, they have this, and you can't even define a constant relationship. Sinusoidal also, it comes and goes, but there's always a limit on how large it can be and how small it can be. But with modulo operators, we can't really say that always. Okay? So Fn and Gn are not comparable if Fn is not an element of big O Gn, and Gn is not an element of big O Fn. Okay? For instance, example is functions involving modulo operators. Okay? So Gn is saying like something mod 2. If we would have a function like this. So it's like, for instance, here, could be here, there, and then decrease again, okay? There is not any typical behavior of the function. So we can't really say that as n goes to infinity, this is the case, okay? With sinusoidal functions and, okay. Now I will give some names for some of the complexity classes that are used frequently. They have specific names and popularly used classes, let's say. And when we say this class, everybody knows what we mean. Popularly used classes. Fastest one, big O one, we say that it's constant order. When we say constant order, we imply big O1, and we usually have it in the best case complexity analysis. And if an algorithm has big O1, then I mean it's really I don't even know such an algorithm. Constant order, we use it usually we encounter it in best case complexity analysis. It might be the case, okay? Another one is big O log n, or big O log n to the power 1.5, okay? These are actually very, very fast. We say them as polylogarithmic. Polylogarithmic order means like log. It's like the logarithms polynomial kind of, okay? Like we can have take three logarithms. These are so close to constants that if you end up with, like in the best case analysis also, some complexity like log n, then you can be, there is a good reason to be suspicious that maybe even constant time is possible, okay? Because it's so close to constant time that it might give you the heads up for saying that, okay, maybe you may even try to prove constant time if you end up with such a complexity. That might even be possible, okay? The second one is, we'll see also in this class, and you already know, logarithmic order. When we say logarithmic order, for instance, what you remember most probably a complexity class for logarithmic order, an algorithm with log n complexity. I don't like sleeping students, okay? I know it's tough to stay awake, but just tell me an algorithm that you already know of from your data structures. Excuse me, I need to take this because it's important. Logarithmic order. And you had time to think about it a little for 5-10 seconds. Which algorithm? Not sorting algorithms, no. They are n log n.
Binary search, binary search
Yes,
tree.
online
search.
classes. More awake than you guys. It should have been reversed, but binary search. But I think a few of you, or at least one of you, mentioned binary search has logarithmic complexity. Searching, not sorting. So, and another, maybe we should mention, base of the logarithm is irrelevant in algorithm analysis. Why? Because it just contributes as a constant factor, the difference between the two. Log base an is equal to log base ab times log base bn for ab greater than 1, okay? And this part is only a constant. So logarithm base 2 or logarithm base 10, whatever, are not important for us. But because we're in computer science, when we say logarithm, we most of the time imply base 2, okay? As is the case with binary search, because we divide it into 2 usually, even in the algorithms mostly. Okay, in general, we imply base 2. So if it's not explicitly mentioned, it means base 2 in complexity, in computer science, which is not the case in general mathematics, okay? But as far as this algorithm analysis is concerned, there is no difference between the two anyway, okay? So we don't care. You could write base 2, you won't write, but if we ask for an explicit and precise analysis, then maybe you need to mention these base 2s if it's really important, okay? If there is a difference between base 2 and 10, then you need to mention it. But in general, for the algorithm analysis, that is not important. Okay, and this is encountered frequently, let's say. And we said constants, log n, which is encountered frequently. And now after log n, the second most frequent, no, okay, but big O n to the power a for a between 0 and 1, okay? It's not n squared. It could be n to the power 1 over 2, and the most famous of this class is big O square root of n, which means n to the power 1 over 2. Okay? So, in general, and we can prove that which one grows faster. Okay, let's see, n to the power a or logarithm n. If a is less than 1, of course. If a is greater than 1, we already know the answer. But square root of n or logarithm of n. Let's try to prove it, okay? I'm giving you the result that n to the power a grows faster than log n. Okay, this is not, I'm just giving you a rough definition, but consider, for example, we should prove it for every a between 0 and 1. But let's say that consider a 0.01, okay? It could be anything, but let's consider that. So it means, like, consider n to the power 0.01. We can use the methods that we have seen. We can take the limits, okay, and take their ratio. Limit as n goes to infinity, n to the power 0.01 over logarithm n is what? Infinity over infinity. So we need to use L'Hopital, right? L'Hopital's rule. So what happens if we use L'Hopital's rule? We take the derivative. Luckily, they are both differentiable. So derivative of n to the power 0.01 is 0.01 times n to the power minus 0.99, right? Over, what is the derivative? We can think of it as ln n base e, because it doesn't matter for us. Base, so we can say that it's just 1 over n, because otherwise we would just have some constant here. It wouldn't matter. So the derivative of ln n is 1 over n. So it's what? It's actually equal to limit as n goes to infinity 0.01 times n to the power 0.01, right? Just observe here that instead of 0.01, we could have written little a. It wouldn't change. As long as little a is less than 1, it wouldn't change. But it's just, we just written 0.01 for you to be able to see what happens more explicitly, because this is just the first example, okay? But this is not the in general proof. This is just the proof of for n to the power 0.01. In general, we want to prove it for n to the power a, where a is between 0 and 1. So which is what? Infinity, right? So if it's infinity, what does it mean? N to the power 0.01 is bigger, like it grows faster. Okay? Therefore, this is like the shorthand notation for therefore. N to the power 0.01 grows faster than log n.
Was 0, then this
Which was 0 if
the answer was 0.
okay, it would mean the reverse. Yes, exactly. Yes, yes. Grows faster than log n, and therefore n to the power 0.01 is in log n. Okay, so log n is a lower bound for that. The other complexity is big O n, linear order used frequently. When we say big O n, or when we say linear order, we actually imply linear big O n. I mean, I'm also so much used to saying linear order. Then big O n, theta n, that's linear order. And for instance, what can be a linear order? If we are given a list of numbers, for example, and we need to scan the entire list, then it's linear order, right? For searching, if we make linear search, that's why it's called linear search, not binary search, but Even if it's not searching, if it's something else, and I need to make a linear search, scan the entire list, then it would be linear order. Okay. The next one is big O and log n. Now this is what happens in most sorting algorithms. Of course, there was insertion sort, you remember, which was n square, but quick sort, merge sort, all the other sorting algorithms you have seen in data structures, they are of complexity n log n. And this is actually typical in divide and conquer algorithms. Which has a catchy name. No, larger. It's no, not faster. Yes, slower than ON. Yes, we are starting from the faster to the slower one now. Okay, and then in the end, I will write a big set of relations between all these complex functions that are used most frequently, starting from O1 to the exponential ones that we will see. Okay. Typical in divide and conquer algorithms, for instance, merge sort, quick sort. These are the ones that you know of. But actually, divide and conquer is an algorithm design technique. Like merge sort and quick sort has this nature, for instance, but there are many other algorithms also that are of this nature. And in the second part of this course, it's one of the algorithm design techniques that we will see. So what properties do such algorithms have, etc. These are the questions that we are going to try to answer in divide and conquer algorithms. Okay, we will also, you will have things like, okay, design a divide and conquer algorithm for this problem, things like that. So quadratic order is n square. When we say quadratic order, we imply n square. Okay, this is typical for algorithms that have two nested loops. Like for instance, for I from 1 to n, and then for j from 1 to n, etc. Okay? These are the algorithms. So big O n cube, we say it's cubic order. When we say cubic order, we imply n cube. Okay? I mean, I just wrote here that pseudocode resemble, if the pseudocode resembles something like this, and I make a constant time operation here, then it's n square most of the time. Okay, like it's like I make a linear scan, and within each scan I make another linear scan, kind of algorithms, like an insertion sort. It depends, and then we need to make an explicit analysis, say that I from 1 to n, from j from I to n, and we will have examples like that. Depending on what happens here, whether it depends on, you need to use your discrete math knowledge there. There is not any direct answer to your question. Okay, you need to you all use these replacements, etc., and find an explicit function in terms of n for the entire thing. It all depends on what happens here. So cubic order. Okay, now big O a to the power n. For a greater than 1, this is exponential order. This is one of the things that you get confused a lot in the exams. You're given an exponential function, but you think that, okay, you're given something like 2 to the power n, but you treat it like n square. And then you try to take the derivative as, okay, what's the derivative of 2 to the power n? You need to remember, you have to, okay? Nobody is going to give you those answers in the exam. But if I see an answer like n times to the power n minus 1, and unfortunately I see them a lot for the past, I don't know, I'm teaching this class for maybe 7 years. I mean, I've been here for 10 years, but something like that, for 7 years or so. And I see it, unfortunately, almost every year, even in online exams. So even then, so I don't want to see it this year. I see it every time, but please remember how to take the derivatives, okay? If you didn't learn it when you took the math, which you should have, learn it now, okay? I'm not going to teach them to you, and your STA also is not going to teach them to you while grading your homeworks, okay? And it's not just some small mistake that everybody could have done. You're going to be engineers, okay? You're not anybody. So big O a to the power n, this is like exponential order. And exponential grows faster than polynomial. So a to the n. Like when you say, for instance, you said faster, but the function growing faster means that the program is is slower, okay? The wording there is important. That's why I said first. For instance, a to the power n grows faster than n to the power a, but an algorithm that has complexity n to the power a is much better because the program having, or the algorithm runs much faster actually for that. But the function growing faster is like, there is a function that blows off, okay? So this is like an algorithm with very slow algorithm, okay? With very high complexity. So a to the power n, which is exponential function, grows faster than n to the power a. But of course, an algorithm that is of exponential behavior is a very slowly running algorithm. Okay. A to the power n grows, the function a to the power n grows faster than n to the power a. For instance, complexity of towers of Hanoi is 2 to the power n, okay, which is exponential. That's why it's a very difficult problem. So another remark, maybe I should remark that also, and then next week we will continue with the other exponential complexity classes. A to the power n, a to the power square root of n, a to the power log square n, like this means like log n, okay? It's not the square of log n. Otherwise, I would have said log n square, okay? Log square n is log n, which is different, okay? This is polylogarithmic, that's what we have said, log to the power. When I take the power to log, I imply that I take logarithms multiple times, multiple logarithms. But this is not like taking the logarithm and multiplying it with itself. Okay, they are different things. Also pay attention to that when you're taking derivatives. Okay, so a to the power are also exponential. So the power does not have to be n. Because as long as it's a function of n, be it a square root of n, it's sufficient to make that an exponential function, okay? As long as the power is not a function of n, it doesn't have to be explicitly a to the power n. It could be a to the power n square, which is even worse, of course, from a to the power n, because n square already grows faster than n. But even these functions are also exponential, okay? A to the power square root of n, a to the power log n. Even a to the power log n is exponential, even though log n is closer to linear, but it's a to the power, has more complexity than a to the power n. It grows faster, but they're also exponential. Okay. Time is off, I think. Uyudunuz mu? Ne oldu böyle? Hani kımıldayamıyorsunuz dün. Hadi bir an evvel gidelim gibi. Hani herhalde trene yetişme şeyi vardı, bilmiyorum. Şu anda hani kalsak daha ders yaparmışız gibi ya da öyle daldık gittik, bilmiyorum yani falan. Böyle iyiydi yani uyumak şeklinde. Online class, we finished the class without any technical difficulty, which is the first this semester. Haftaya görüşürüz.
İyi günler hocam.
İyi günler hocam.
Bir şey soracağım. Samet, bir şey soracağım. Yok yok, durdurma.